Hello fellas, today I'm going to talk about the cross product. So what is the cross product and why do we need the cross product? So as with any problem in maths, we have to start with a problem. Say we want to find the area between two vectors, let's call that A and call that B. Okay, so let's say there's an angle theta between them and we want to find the area of the parallelogram that they form. Okay, so we know from geometry that the area is going to be the base times the height. We're marking the height sort of like that. The height's going to be perpendicular to A, and we know that it's going to be mod A, which is the size of A, times the height. Call that H. Okay, so we can sort of move this in closer here so that we get this, and that's still H. And we can see that H is simply B sine theta, and therefore our area is mod A mod B sine theta. Okay, everything looks good, but we don't like angles. Well, I don't like angles, so let's go and derive the cross product, which will actually not just give us the area, but will also give us a useful way of finding normal vectors to A and B. Okay, so how do we proceed? Well, we can draw in H as a vector, because that's useful, and we can sort of separate this A vector into, well, not really separate, but sort of divide it into this lambda A vector. Okay, and we can see that H is simply going to be B minus lambda A. Okay, well, we'll come back to that later. Okay, so now that we've defined H as a vector, we can sort of write the area as so. And we know that the magnitude of a vector is going to be the following. It's just going to be the sum of the it's going to be the square root of the sum of the squares of the components. Hope I said that right. Okay, now I'm just gonna multiply everything. I'll probably fast forward this part because it's quite boring to watch me multiply. Okay, so we have this big square root. Okay, so I've deliberately put these sort of corresponding terms together because if you look at it, you can see, well, with some practice, that you could write this as A1H1 plus A2H2 plus A3H3 squared. Well, let's write it like that, and that's going to be plus these terms where I have A1, A1, A2, H1, H2, and A1, A3, H1, H3, and we have A2. Well, if I multiply this by this again, I'm going to get twice that, and we'll see that when we do the third one, it's going to be something like that. And we'll also get twice A2, A3, H2, H3. Okay, so that's very nice. So what we want to do is we want to substitute for this in terms of that and that. But why? The answer is that we know that H and A are perpendicular. We have a 90-degree angle there, and we know that the dot product, if we take the dot product of A and H, we're going to get this. Which is what's in there, if you can see that. Which is going to be, if you know dot products, cause let's call that phi. Phi because it's not theta, it's the angle here between A and H, not A and B. Okay, so we know that phi is at 90 degrees, and cos 90 degrees is 0, and therefore that's 0. And very conveniently, we can substitute for 0 there, and therefore we're going to get A1H1 squared plus A2H2 squared plus A3H3 squared is going to be negative twice A1A2H1H2 minus 2A1A3H1H3 minus twice A2A3 H2H3. Okay. Okay. So now we can use these terms here. Let's see what we get when we combine. If you look at these subscripts, 1, 2, and we also have another one, 2, 1, that sort of looks like we could probably factorize that. So let's just write one term in. So A1H2 squared. We're just writing the term for 1 and 2. So that's going to turn out to be and we can see that that is going to be A1 H2 minus A2 H1 squared. Now isn't that lovely? Okay, so we can really just substitute. Let me get another piece of paper. We can substitute for that, for this big square root over here, which is the area, of course, in terms of these little terms. So mod A mod H is going to be the square root of A1H2 minus A2 H1 squared plus A1H3 minus A3H1 squared plus A2H3 minus A3H2 squared. Okay, now we want everything in terms of A and B because we don't really know H. We just know about A and B. That's what we're given in our question. Finding the area between A and B. So remember I said that we could write H as B minus lambda A. So let's do that. So what this means for a given component is going to be something like H1 is going to be B1 minus lambda A1 Okay, so let's see what happens when we substitute for one of these terms, so that we can then generalize for each of the terms. So a1h2 minus a2h1 is well, squared. It's going to look something like a1 multiplied by, so h2 is going to be b2 minus lambda. Okay, my phone just died on me. Sorry about that. Let's get back to it. So we're substituting this into this, sort of the h2 component. Lambda a2. What are we doing? Yes. Okay. So lambda a2. Okay. Minus a2 b1 minus lambda a1. That's going to be all squared, which is going to be, so that's going to be a1 b2. We'll take that term, a2 b1, and we're going to have minus lambda. We'll take lambda out. We'll put a1 a2 there, and because we have a positive sign here, we need a negative sign so that we make that positive. a2 a1. We have a square. So you can see that the lambda term sort of disappears because we have a1 times a2 minus a1 times a2, which is going to give us 0. So this term is going to become a1 b2 minus a2 b1 squared. That's excellent, because that looks exactly like that, except with b instead of h. Okay. Square root of a1 b2 a2 b1 squared plus okay. Now this thing here looks quite familiar. In fact, it is exactly the determinant, the 2 by 2 determinant of this determinant. So that's going to be a1 b2 minus a2 b1. So we sort of have this sort of mod of, as in the magnitude of, some vector that has components like this. Okay. Now we can even simplify this further, and well, not really simplify, but let's see. So we could say there's a vector d that which has components d1, d2, and d3. Then we could have this determinant of 3 vectors. We have d1, d2, d3, a1, a2, a3, and b1, b2, and b3. And that is going to be d1 times this determinant, which is a2, a3, b2, b3, minus d2, a1, a3, b1, b3, plus d3, a1, b2, a2, b1. Okay, so imagine, now we can see that this is a magnitude of a vector, clearly. So if the vector had components of these determinants, then it would have, say, we could substitute, instead of d1, we could have, say, for example, I, because a vector with components these would be something like this. And therefore, so we have this magnitude of some vector, which is going to be equal to mod A mod H. Now, when I say that there's a magnitude of some vector that is equal to this, what I mean is because there's a square root and a sum of squares of components, seemingly, we could say that there's a vector. We'll call it, say, n hat. That is going to be, so n hat times its magnitude is going to be the full vector, which is going to look like that. So we can say mod A mod H is going to be equal to, let's write this as mod A mod B sine theta, because mod B sine theta is the same as mod H, n hat. And this is, we'll call it A cross B, because that's the definition. The definition of A cross B is going to be mod A mod B sine theta n hat. And the property of this n hat is that it will be perpendicular to both A and B. So that's sort of a corollary. And finally, we could write this in its determinant form, which will just be ijk a1, a2, b3, b1, b2, b3. And that's our answer. So if you were confused as to how we got this determinant, this was what the video was for. Hope you enjoyed. Thank you for watching, and have fun with maths.